Linear partial differential equations of first order. Definition is a differential equation which involves the partial derivatives p and q only. So p and q are first order partial derivatives. P is dou z upon dou x and q is dou z upon dou y. And no higher order derivatives is called a first order equation. So equation involves only p and q's and no higher order derivatives. Higher order derivatives means R, S, T. These are higher order derivatives, second order derivatives. So equation here involving only P and Q. And having degree 1, it is called linear partial differential equation. For example, if you see the example 1 here, Px plus Q y square is Z. Here, the equation involves only P and Q having degree 1, so that it is called linear partial differential equation. But see the example 2, here the equation involving P and Q, PQs are first order partial derivatives, but P and Q are having degree 2. If the equation having more than degree 1, then it is called non-linear partial differential equation. Now, linear partial differential equation means a differential equation which having only p and q and degree 1. It is called linear partial differential equation. Otherwise, it is called non-linear partial differential equation. Now we will have a Lagrange's equation. So it is a general form for first order partial differential equation. A linear partial differential equation of order 1 involving a dependent variable z and two independent variables x and y, and is of the form pp plus qq equal to r, where capital letters PQR are functions of xyz is called Lagrange's linear equation. So it is the general form of Lagrange's equation where capital letters PQR are functions in terms of small x, small y, small z, and small pq's are first order partial derivatives. That is, small p is dou z by dou x, q is dou z by dou y, where z is a dependent variable and small x, small y are two independent variables. Now to get the solution of linear equation of the form PP plus QQ equal to R. Once again, what is the PP plus QQ equal to R? It is called Lagrange's linear equation. Now to solve this Lagrange's linear equation, first we have to write auxiliary equations. Auxiliary equation is dx by p is equal to dy by q equal to dz by r, where capital P, capital Q are the coefficients of small p and small q, which are in terms of x, y, z, and capital R is the right side of the equation, which is also in terms of x, y, z. So it is called auxiliary equation to the linear equation. So here the linear equation PP plus QQ equal to R is called Lagrange's equation. Now we will have two cases to solve such type of Lagrange's linear partial differential equation. If possible to separate the variables, then consider any two equations, solve them by integrating. Let the solution of these two equations are u equal to a, u equal to b. Hence the solution is phi of u equal to 0 is the required solution of the given equation. So here just we have to separate the any two equations and we have to solve them just by taking the integration or applying integration on both sides. We will get two different solutions, and they are u equal to a and u equal to b, where ab's are constants. Thus we will have a complete solution of the Lagrange's linear partial differential. Thus, we will have a solution for Lagrange's linear equation, that is phi of uv equal to 0 is the required solution of the given Lagrange's linear equation. So just we have to separate the equations, any two equations, we have to get two different solutions just by applying integration on both sides. The two solutions are kept as phi of uv equal to 0. So which is the required solution for the given Lagrange's linear equation is in the form pp plus qq equal to r. Suppose if it is not possible to separate variables, so it is the Lagrange's equation. It is the auxiliary equation of the Lagrange's equation. Now to solve this problem, we have the following methods. The first method is method of grouping and another method is method of multipliers. In some problems, if it is possible to solve any two equations, dx by p equal to dy by q, dy by q equal to dz by r, dx by p equal to dz by r, so that the first two terms are equated, next two terms are equated, first and last term, first fraction and last fraction is equated. So we can solve these equations, any two equations separately, so that we will get a solution and then substitute in the other differential equation, we can solve the differential equation. So it is known as a method of grouping. Once again, we have to equate like this. First two fractions are equated, middle and last fraction is equated, or first and last fraction is equated, and solve the differential equation, get the solution and then substitute in the other differential equation. We will get the solution for the given linear partial differential equation. Next one is method of multiplier. Consider dx by p equal to dy by q equal to dz by r. In this case, we will take an extra fraction, that is ldx plus mdy plus ndz upon 0, where lmn are multipliers. We have to choose these multipliers so that the denominator should be 0. If it is 0, then we will get a solution just by integrating the numerator, that is ldx plus mdy plus ndz. It will be integrated, thus we will get the solution for the required Lagrange's linear partial differential equation is in the form pp plus qq equal to r, where capital P, capital Q, capital R are functions of xyz and small p, small q are first order partial derivatives, that is p is dou z by dou x and q is dou z by dou y. Don't forget, if the equation is not possible to separate the variables, we will use method of grouping and method of multipliers. And coming to non-linear partial differential equations. A partial differential equation which involves the first order partial derivatives p and q with a degree higher than 1, that is more than 1. The equation contains first order partial derivatives. The first order partial derivatives are pq's, not RST. RST are second order partial derivatives. And the products of PQ, which equation involves the products also, PQ products, PQ, P square, Q square, P cube, Q cube, like, is called non-linear partial differential equation. Once again, the definition is a partial differential equation which involves the partial derivatives P and Q with degree higher than 1, and the products of P and Q is called non-linear partial differential equation. A partial differential equation which involves P and Q with a degree higher than 1 and the products PQs is called a nonlinear partial differential equation. Now to solve nonlinear partial differential equation, we have 6 types. The types are: first type is equation involving only PQs of the form f of PQ equal to 0. Second type is equation of the form f of PQZ equal to 0. That is the equation involving Z also. Type 3. Equation is of the form f1 of p comma x is equal to f2 of y comma q. This method or type is also known as variable separable method. f1 of p comma x is equal to f2 of y comma q. Next, coming to type 4, that is Clairaut's form. So Clairaut's form is z equal to px plus qy plus f of p comma q is known as a Clairaut's form. Next, type 5, equations reducible to standard forms f of x power m p comma y power n q equal to 0, f of x power m p y power n q comma z equal to 0, and f of p z power m comma q z power m equal to 0, and f1 of x p z power m equal to f2 of y comma q z power m. These equations are reducible to either type 1 or type 2 or type 3. So it is type 5. Next type is Chartbased method. It is the last one, type 6. Let us see all in detail. First one is f of pq equal to 0. Equation of the form f of pq equal to 0. That is equation containing p and q only. Let the required solution be z equal to ax plus by plus c. In this, first of all, we have to define the complete solution of the non-linear partial differential equation. That is z equal to ax plus by plus c. We will have dou z by dou x is a, dou z by dou y is b, which is obtained by differentiating partially with respect to x and y. Substituting these values in f of pq equal to 0, and we get f of a comma b equal to 0. So f of p comma q equal to 0, just we have to replace p as a and q as b. Thus we will get the equation. From this equation we have to write b in terms of a. That is b equal to phi of a. And then substituting this value in the defined complete solution. Thus we will have z equal to ax plus b. But what is b here? Phi of a. So phi of a into y plus c. Don't forget the complete solution obtained equation must and should have only two constants. Those are a and c. Since the given equation contains two first order partial derivatives p and q, the final solution should contain only two constants. So what are the two constants here? A and c. So easy procedure. If the equation contains f of pq equal to 0, that is equation having only p and q's, first of all we have to define the complete solution, that is z equal to ax plus by plus c. And then we have to replace p as a and q as b in the given equation. Thus the equation becomes f of a comma b equal to 0. From this equation we have to write b in terms of a, and then we have to replace b in terms of a in the defined complete solution, which gives the required complete solution of the given equation, which is in the type f of p comma q equal to 0, where pq's are first order partial derivatives. And also note that the obtained last complete solution equation, which contains only two constants, those constants are a and c. Nonlinear equations type 2. Suppose the given equation is f of p, q, z equal to 0. That means the given equation contains only p, q and z. In such a case, we have to take the complete solution which is defined as z is function of u. That is z equal to f of u or z equal to z of u, where u is x plus ay, where x, y's are two independent variables and z is a dependent variable. The complete solution is defined as z equal to z of u. Now computing the first order partial derivatives PQs, P is dou z by dou x. It can be written as dz by du into dou u by dou x using chain rule. But dou u by dou x value is 1. Thus we will have P is dz by du. Similarly, Q is dou z by dou y, but it can be written as dz by du into dou u by dou y. But dou u by dou y value, that is differentiating u partially with respect to y, we will get a, because x derivative is 0, ay derivative a. Thus we will have q value is a dz by du. Don't forget these values. P is dz by du and q is a into dz by du. Substituting these values in the given non-linear partial differential equation, we will get the new equation is in the form Pf of dz by du a into dz by du z equal to 0. That is, equation contains only z as a dependent variable, u as independent variable. Now we can solve this equation using separation of variables, and then we have to replace u as x plus ay. So don't forget to replace. Finally, we have to substitute u as x plus ay, which gives the required complete solution. So once again, the given equation contains only pqz. The complete solution, first of all, we have to define as z equal to function of u, that is z equal to f of u or g of u or z of u, where u is x plus ay, and we have to remember these values must ensure, that is p is dz by du and q is a into dz by du. These are replaced in the given equation. Thus we will have a new equation z in terms of u. We will get the complete solution look like z as in terms of u. At the end of the solution, we have to replace u as x plus ay. Now type 3. So type 3 is a variable separable method. That is f1 of p comma x is equal to f2 of y comma q. That is p and x are one side and y and q are other side. That is p and x are quietly separated with q and y. This equation is equated to a constant, that is a. So f1 of p comma x equal to a and f2 of y comma q equal to a. From these equations, we have to write p in terms of x and q in terms of y. Now we will have the total derivative formula, that is dz is dou z by dou x into dx plus dou z by dou y into dy. But dou z by dou x is a p and dou z by dou y is a q. Just replace pq values. What is p here? P is psi 1 of x and q is psi 2 of y. Thus we will have a new equation, that is dz is psi 1 of x into dx plus psi 2 of y into dy. Now integrating this equation, we will get the required solution. So easiest method, this method is useful only when the variable must and should be separable, and p and x are one sided and q and y are other side. P and x are quietly separated with q and y, then only we can apply this method. In this method, just the arbitrary constant is equated to this equation, so that we will have p in terms of x and q in terms of y. These are replaced in the total derivative, and then integrating, we will get the required complete solution for the given partial differential equation. This method is also known as variable separable method because p and x are quietly separated with q and y. Type 4, Claridge's form. The Claridge's form is easiest one. The Claridge's form is z equal to px plus qy plus f of p comma q. The complete solution is defined as z equal to ax plus by plus c. Dou z by dou x is a, that is p. Dou z by dou y is b, that is q. So p equal to a and q equal to b. Replacing p and q values in the given Claridge's equation, thus the equation becomes z equal to ax plus by plus f of a comma b. It is the required solution for the Claridge's equation. So very easiest one, directly substitute a in place of p and b in place of q in the given equation. So we will get the complete solution. The Claridge's equation, just we have to remember this equation, that is z equal to px plus qy plus f of p comma q. Here the complete solution is obtained just by replacing p as a, q as b, which gives the required complete solution, that is z equal to ax plus by plus f of a comma b. Now type 5 equations reducible to standard forms. The standard form is f of p comma q equal to 0, that is type 1. Now the given equation is f of x power m p y power m q equal to 0, where m and n are constants. Let us transform this equation to the form, that is type 1 f of p comma q equal to 0. Here cases are arises. Suppose when m not equal to 1, n not equal to 1. In this case, we have to put capital X as x power 1 minus m and capital Y as y power 1 minus n. And we will have a partial derivatives, that is p and q. P is a dou z by dou x and q is a dou z by dou y. But dou z by dou x can be written as a dou z by dou capital X into dou capital X upon dou small x. That is, but dou z by dou capital X is capital P and dou capital X by dou small x is 1 minus m into x to the power of minus m, because 1 minus m into x to the power of 1 minus m minus 1, 1 get cancelled, we will have x power minus m. Similarly, we will have q, that is capital Q into 1 minus n into y power minus n. Now substituting these values in the given non-linear partial differential equation. Now this will be transformed to the form f of pq equal to 0, that is f of capital P comma capital Q equal to 0, that is type 1. We have already solved type 1, thus the type 1 problem is solved. We will get the solution. At the end of the solution, don't forget to replace capital X as x power 1 minus n and capital Y as y power 1 minus n. Suppose in case of m equal to 1 and n equal to 1, here the substitution is capital X is log x and capital Y is log y. And P is a dou z by dou x, Q is a dou z by dou y, which are obtained similarly as above. That is, a dou z by dou x can be written as a dou z upon dou capital X into dou capital X upon dou small x. But dou z upon dou capital X is capital P. Dou x by dou small x is log x derivative 1 by x. Similarly, we have small q value is a capital Q by y. Thus, we will have small p is replaced with capital P by small x and small q is replaced with capital Q by small y. Thus, we will have a new equation, that is f of pq equal to 0. This is known as the type 1. So, solving this equation using type 1, at the end of the solution, we have to replace capital X as log x and capital Y as log y, which is the required complete solution. So equations of the type f of x power m p y power m q comma z equal to 0, where m and n are constant. This equation can also be reduced as the same as above. Just we have a extra term, that is f of p q z equal to 0. It is known as type 2. Taking the same as above substitutions. That is, this equation becomes type 2, transformed to type 2. And equations of the form f of p z power n comma q z power n equal to 0, where n is a constant. Suppose the given equation, given non-linear equation, this is of the form look like this. So in order to convert the given equation into the standard form 1, here we have to replace z as z power n plus 1 and capital Z as log z. So this will be used when only n not equal to minus 1. This will be used when n equal to minus 1. Now equations of the type f1 of x p z power n is equal to f2 of y comma q z power n, where n is a constant. Now this type of equations are also reduces to the form type 1. or f1 of p comma x is f2 of y comma q by taking above substitutions given for the equation f of p z power n comma q z power n equal to 0 where n is constant. Once again, if the given equation look like this, then this will be converted or transformed to the form, the standard form f of p comma q equal to 0 or f1 of p comma x is equal to f2 of y comma q. This will be done by the substitution of z as z power n plus 1 whenever n not equal to minus 1 and log z whenever n equal to minus 1. Then while using these substitutions, the equation becomes either type 1 or type 3. Now, Charpit's method, last method, that is a type 6. So it is very useful method. It is a general method to find the complete solution or complete integral of the nonlinear partial differential equation. It is in the form f of x, y, z, p, q equal to 0. That is the equation involving x, y, z and p, q's also. So here we have to remember this formula, that is the auxiliary equation of Charpit's method. The formula is dx upon minus dou f by dou p is dy upon minus dou f by dou q is dz upon minus p dou f by dou p minus q dou f by dou q, dp upon p dou f by dou z plus dou f by dou x, dq upon q dou f by dou z plus dou f by dou y. Without this, we can't do anything. So here, using any one of the equations or any one of the fractions are equated so that we can calculate p and q easily. So here we have to take the terms whose integrals are easily calculated so that it may be easier to solve for p and q. So obtained p and q are in terms of x, y, z. These are substituted in the equation dz equal to p dx plus q dy. And then we have to take or choose readily integral combinations while grouping the terms and then integrating the equation. We will get the required solution of the given partial differential equation which having not only x, y, z, which having p, q's as a first order partial derivatives. Note that important point is the above five types of problems can be easily solved by using this type, that is Charpit's method. So above types means, once again, first type is of the form f of p comma q equal to 0, that is equation contained only p q's. Second type is equation having PQZ, f of PQZ equal to 0. Third type is variable separable method, that is P and X are quietly separated with Q and Y. And type 4 is Claridge's equation, that is Z equal to Px plus Qy plus f of P comma Q. And type 5 is equations reducible to the standard forms, that is a type 1 or type 2 or type 3. Last one is Charpit's method. So this is about linear and non-linear partial differential equations solving. So in linear we will have two methods, that is method of grouping and method of multipliers. In non-linear equations we have six types. In next class we will do the problems related to linear partial differential equations and non-linear partial differential equations. Thank you.